Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever feel like you're not quite sure if the connections you see between things are real or just in your head? Well, today we're diving into a fascinating new study that tries to untangle the real connections between things in complex systems, especially in psychology. Imagine the human mind as a giant spider web, where each point is a thought, feeling, or behavior, and the threads connecting them are the relationships between them. This is kind of what psychologists mean when they talk about Gaussian graphical models. They're like a map of all these connections. The big problem is figuring out which connections are actually important and which are just noise. Most of the time, scientists use a method called L1 regularization. And this paper argues it has a big flaw. It tends to shrink all the connections equally, meaning it can underestimate how strong some important connections are and miss others entirely. Think of it like trying to sharpen a photo but accidentally making everything a bit blurry. In psychology, understanding how different thoughts or feelings are connected is super important. It helps us understand things like why someone might feel anxious or depressed. These connections are called edges, and how strong they are tells us about how important a particular thought or feeling is. But the tools scientists have mostly used, like L1 regularization, which is a technique to simplify complex data, have a problem. They try to simplify things by making the less important connections weaker, but they often make all connections weaker, even the really important ones. This can lead to mistakes in understanding how things are truly linked. So these researchers decided to look at a huge collection of psychology studies, a ton of them, 290 to be exact. They wanted to see what patterns they could find in the raw data before any fancy math was applied. They looked at something called partial correlations. Basically, this is a way to measure how strongly two things are related while accounting for the influence of other things. Think about it like this. You might think talking on the phone makes you a worse driver, but maybe the real reason is that when you're on the phone, you're also more likely to be stressed. And stress is what makes you a worse driver. Partial correlations try to isolate just the phone call effect. When they looked at the data from all these studies, they noticed something really interesting. The patterns of these partial correlations, especially the strong ones, seem to follow a specific mathematical shape. Specifically, the data often fit what is called a Weibull distribution really well. This is a type of distribution that comes from something called extreme value theory, which is basically the math behind figuring out how often extreme events happen or how things behave at the edges of what is normal. So they thought, what if we use this natural pattern, this Weibull distribution, to help guide our math when we're trying to build these network maps? Instead of using a one-size-fits-all approach that might blur important connections, what if we create a method that adapts to the specific data we're looking at? They decided to create new ways to build these network maps using not just the Weibull distribution, but also related ones like Gumbel and exponential. The main idea is to make the math adjust itself to the unique noise level or the background randomness in each specific dataset. Think of it like tuning a radio. Instead of just setting the dial to a fixed frequency, these new methods help the radio tune itself to the strongest signal in each dataset. This also means they can better approximate what is called the zero norm penalty, which is like a perfect system for picking out only the truly important connections and ignoring everything else. It's the ultimate sharp photo. They developed specific mathematical formulas called penalties based on these distributions. These penalties are applied when building the network map. The goal is to encourage the mapping process to zero out the weak or insignificant connections while keeping the strong ones. The key is that these penalties are not fixed, they're data adaptive. This means they change their behavior based on the characteristics of the data they're analyzing. This adaptivity is crucial. For example, they found that the parameters of the Weibull distribution, which describe its shape and scale, can be directly related to observable statistics of the partial correlations in the data, like the average strength of those correlations and how spread out they are. This means they can estimate these crucial parameters directly from the data, making the whole process much more grounded and less reliant on guesswork. The big question the study wanted to answer was simple: does using these new data adaptive methods actually lead to better, more accurate maps of psychological networks compared to the old standard methods? They tested their approach against other popular methods, including the commonly used Ebiglasso and Bayesian GGMs, as well as other non-adaptive penalties. They ran a giant simulation using different kinds of network structures and sample sizes, from small groups to very large ones. Imagine building many different kinds of city maps. Some maps were designed to show clusters of neighborhoods that are very connected within themselves, but less connected to other areas like a stochastic block model. Others were designed to show more interconnected cities where even distant cities are surprisingly close by, like a small world network. They tested how well each mapping method could recreate these different city plans with different numbers of people or variables involved. They wanted to see if their new methods could pick out the correct roads and ignore the dead ends better than existing methods. And they found some really significant patterns. Across the board, with bigger sample sizes, pretty much all the methods got better at figuring out the true connections. But the old reliable method Ebiglasso, which is super popular, wasn't as good at ignoring fake connections. The ones that looked real but weren't, even with more data, it kept picking up connections that weren't actually there. Think of it like trying to identify all the important people in a crowd, but you keep thinking random strangers are important too. On the flip side, their new adaptive methods, especially the Weibull one, were really good at being specific. They were great at ignoring fake connections, and as the sample size grew, they also got better at picking up the real important connections. It is like having a super precise detective who doesn't waste time on false leads, but still finds all the actual culprits. Let's look at the results broken down by the type of network. In the clustered network models, the older methods tended to either miss important connections or include fake ones. But the adaptive methods, especially Weibull, showed a better balance. They were more precise, meaning fewer fake connections, and as they got more data, they became more sensitive, picking up more of the real connections too. The same story played out in the small world networks. The new adaptive methods consistently outperformed the older ones, especially when it came to avoiding false positives. This means the connections they identified were more likely to be the real deal. One of the key things these network maps help us understand is which parts are most important, like the main streets or the busiest hubs in a city. This is called centrality. The paper found that the old methods, by making some connections weaker or adding fake ones, could really mess up our understanding of which parts were truly central. The new adaptive methods, because they were better at picking out the real connections, also gave a more accurate picture of what was truly important. They measured how well the rankings of importance matched the true rankings. The adaptive methods, particularly Weibull, consistently achieved excellent rankings, meaning they were really good at identifying the most important elements in the right order. To see if this translated to real-world data, they looked at a massive personality dataset. They used this data to see how often different methods picked up the same connections when looking at parts of the data. They found that the Weibull method often sat in the middle, agreeing with both the highly sensitive but sometimes error-prone Ebiglasso and the highly specific but sometimes slow-to-find Bayesian approach. It was like a consensus builder. When they compared the actual network maps from different methods on this real data, they saw big differences. Some connections were found by all methods, but many were unique to one method. This showed that the choice of method really mattered for what you concluded about how personalities are connected. For instance, one method might say assertiveness is the most important personality trait, while another might say excitement. Seeking is. The Weibull method often landed squarely in the middle, suggesting it was finding connections that were likely real and important. So, what is the big takeaway from all this? The standard methods, while useful, have limitations, especially with the amount of data scientists collect nowadays. They can miss important connections or claim connections are there when they aren't. The new adaptive methods, grounded in extreme value theory, seem to offer a much better way to build these psychological network maps. They are more precise, meaning they're better at avoiding fake connections, and as they get more and more data, they become more sensitive, picking up all the real connections without getting fooled. The simulation clearly showed that the adaptivity, the ability of the method to adjust to the specific dataset was key, especially with larger amounts of data. It helped the methods get closer to a perfect understanding of the true connections. In the real-world personality data, the Weibull method stood out. It was like a dependable friend who agrees with most people, but also has good insights of its own. It occupied a comfortable middle ground, offering a more balanced and likely more accurate picture of personality connections. This means that for researchers studying the human mind, especially when dealing with limited data, using these new adaptive methods could lead to more reliable and interpretable findings. It's not just about getting a map, but getting the most accurate map possible. The Weibull penalty is recommended as a good default because it is not only effective but also its mathematical parts can be directly understood in terms of the data, making it easier for scientists to explain their findings. Now, no study is perfect, and this one is no exception. They focused on data that was continuous, like measurements that can have decimals. But a lot of psychological data is more like yes or no answers or categories. So, we don't know for sure if these new methods will work just as well for that kind of data yet. Also, while the results strongly suggest these new methods are great, Proving it mathematically with absolute certainty, like proving a theorem, is still an ongoing process, but the evidence they've gathered is very, very strong. Ultimately, this research provides a significant step forward in how we map and understand complex psychological systems. By moving beyond older, more rigid methods and embracing data-adaptive approaches grounded in the natural patterns of psychological data, scientists can build more accurate and interpretable models of the human mind. This can lead to a better understanding of everything from personality to mental health. And a big thank you to all the researchers who compiled the massive dataset this study used. It's through open science and collaboration that we make these amazing discoveries. And the authors report no competing interests, which is always good to see. And all the data and code for this study are available for anyone to look at, which is fantastic for transparency. It is always interesting to see the roles people play in these big projects. Alexander Christensen and Jeongwon Choi were involved in almost every step, from the big ideas to the detailed analysis and writing. They even use some AI tools to help polish the language, which is becoming more common in science. So, what do you think? Does this give you a new perspective on how we study the mind? Let us know in the comments below. If you found this breakdown helpful, please give this video a thumbs up. Subscribe to RUBIN'S Mind Lab for more science explained simply. And hit that notification bell so you don't miss our next dive into the fascinating world of psychology and beyond. Thanks for watching, and we'll see you next time.